Quantum mechanical wave functions are generally complex functions, and this is important for capturing their essential behavior and properties. However, there are several ways that we can translate them into real quantities, and it's useful to review some of those here. For example, we've seen that if we want to interpret what the wave function is, we might construct its square magnitude and then multiply it by a volume element to get something that would be essentially recognized as a probability density. And so this is one way that we can talk about the quantum mechanical wave function as an object that really connects to real life. Okay, it's real by virtue of its square magnitude. Now, we also can think about, for example, the eigenvalue equation for a Hermitian operator, which produces real eigenvalues. Okay, and those real eigenvalues come from the Hermitian property. But we wouldn't have those if we didn't have a Hermitian operator. So the Hermitian operator is something that's needed to connect us to the reality. Finally, for those same Hermitian operators, we can define expectation values, and I'll write this using the special Dirac notation as follows, like this. And we know that this will always end up generating a real quantity also, as long as A is a Hermitian operator. Now, are there other ways that we can also generate real quantities out of complex wave functions? Well, I want to explore one in particular, and that is we can make them be real functions artificially by creating suitable linear combinations of these functions. So, for example, I'll remind you that this complex exponential e to the im phi is actually equal to cosine of m phi plus I sine of m phi. Okay, which means that we can actually create linear combinations of these things that would make them into real functions. So for example, I can define a real function cosine of m phi simply by taking 1/2 the sum of these two exponentials. All right, I could also create sine of m phi by taking 1/2i times the difference of the two exponentials. So there are ways that we can take these complex functions and, in some sense, connect them to reality through real valued functions just by manipulating them in particular ways. Now let me give you an example of how this might help us in a particular case involving hydrogen atom wave functions. All right, we know that the hydrogen atom wave functions for n equals 1 and L equals 1 rather, and m equals 1 would look something like this. I'd have YL, say 1, 1, and that's going to have the functional identity 3/8 pi sine theta and e to the I phi. But if I had made that a minus 1, if I made that plus or minus 1, I would have plus or minus there. So I basically have two complex exponentials that create a complex function here. And if I want to express this really as a real function, then I would need to take a linear combination of the two. So if we do that, and let's just draw what we would have here. If I were to create, for example, the linear combination that looks like this, 1/2 of y11 plus y1 minus 1, well, that would simply be taking square root of 3/8 pi sine of theta, and then this particular combination of these exponentials, 1/2 times e to the I phi plus e to the minus I phi, is going to generate cosine phi, so I'll have cosine phi here. Now, if I were to analyze this particular wave function for its nodal surfaces, as we have done in a recent video, what we would find is that sine of theta is going to have its nodes at theta equals 0 and pi, which we know essentially represents the z-axis in the spherical polar coordinate system. Cosine of phi, however, has its zeros at pi/2 and 3 pi/2, which corresponds to the y-axis. So what that tells us is that for this particular linear combination, I'm going to have a nodal plane that is the YZ plane. And I hope you can anticipate that if the YZ plane is a nodal plane, and let me draw it sort of edge on. So my nodal plane is this plane here, and this is Y and Z, that the axis that's perpendicular to the YZ plane is the x-axis, and that's where all of the wave function amplitude is going to be. So I would end up creating a p orbital that essentially lies along the x-axis. Okay, well that's something that we know of as the px orbital. All right, so these linear combinations can serve us in some great ways to create real functions out of it. I will say that similarly, if I were to take this linear combination 1 over 2i times the difference between these two spherical harmonics, I would end up creating a very similar looking orbital, but now it's got sine phi instead of cosine phi. And I hope that you can anticipate that really what happens when we do this is that we're going to end up with a net function that will be the py orbital. And I want you to try that analysis on your own, separately from this lesson, and see if you can get that the nodal plane for this would be the xz plane. All right, let's finish with a little bit of abstract way of representing some of these orbitals. All right, so sometimes what we need to do is to express these orbitals simply by giving a cross section and showing where the nodal surfaces hit that cross section. So, for example, if I were to create a diagram like this, where this is the nucleus, and I've got a circle around the nucleus and a second circle around the nucleus, and I said that this was a cross section that shows the nodal surfaces, how would you analyze that? What orbital does that represent? Well, it's got 2 nodes total, so we know that the total number of nodes is equal to n minus 1, so that means that for this particular case, I have n equals 3. All right, do I have any angular nodes? Well, in fact, there are no angular nodes here. Both of these are circles, which suggests that they represent spherical surfaces around the nucleus, so they must both be radial nodes. So for that reason, I would say there are 0 angular nodes in this state. So that means that my L value in this case is going to be L equals 0. Okay, well that corresponds to an s orbital. So this would be a way of representing the 3s orbital of the hydrogen atom. All right, now let's try another one. What if I had a case where I've got my nucleus here, and again I've got a circle around the nucleus, but I also have a line that goes through the nucleus. Okay, well the circle once again represents a radial node, but the line now represents an angular node. And the reason I say this is because I've got to change the angle. I've got to rotate around in order to cross this node. I can't cross this node by moving in a radial direction, but I do cross the radial node. So this would be an angular node in this case. And that means that I still, again, have 2 nodes total. So again, my n value is going to be equal to 3. But now I have one radial node and 1 angular node. But it's the angular node I care about because that's directly related to the value of L. So with 1 angular node, that tells me that I have L equal to 1, which is a p orbital. So this, in fact, with a nodal surface that goes around in a circle and one that goes through, this would be a 3p orbital. Okay, lastly, although there's many more I could draw, I'll only draw one more. Let's suppose that I have a nodal surface that looks like this in the cross section. And I haven't drawn that very well, but I hope you can appreciate that what I've drawn here are essentially 2 angular nodes. And there are no radial nodes. So I still have 2 nodes total. So again, I'm going to have n equal to 3. for 2 nodes. But now that I have 2 angular nodes, that means that I have L equal to 2. And that corresponds to a d orbital. So this would be a 3d orbital. And in fact, it could represent, these being the planes, it could represent many of the different d orbitals simply because they would show 2 of these angular nodes. So I present these patterns not because they give you any sort of cosmic new knowledge about quantum mechanics, but I hope they're a way that you can use to visualize these orbitals and understand sort of their essential features simply by analyzing their nodal patterns. And you can be able to see the differences. All of these correspond to n equals 3 states, but they're very different from one another. 3s, 3p, 3d. They have different nodal patterns, and they'll look different in space if we were able to actually see them with our eyes.